Hello guys, how are you? So today we are going to see like whenever you are fine tuning any small language models and at the end if you want to deploy that model to the productions or even if you want to utilize that model set into the GPU machines, then within the short GPU memory, how you can deploy those models and how you can utilize those efficiently. So by taking the help of vLLM, how it's working, what is the working principle behind it, as compared to the other methods, and because of that how it's improved the working of those models and all those things, reductions of latency and all those things. So we are going to say those in details into the given video. So we are going to see some few techniques here, like why is serving LLM so challenging, because you can do the fine tuning but why it's challenging if it's going to the productions and all those things. What is vLLM, then what is PLLM secrets or what's the behind working it's all those things, and also we will going to see some demo. Then better way I will start to share my screen so that you can see all those things very well. So I will initially give few things related to the VLMs and all those things. So one of the most important factors and critical factor is the computational resources. Whenever you are fine tuning any small language models and when you are trying to utilize it or run it in your own machines or either in the GPU machine, so the cost of those computational resources is very high. Even if you are going to purchase GPU laptops, then you can see the difference as compared to the others laptops. So, due to the fact that LLM has the numerous parameters to perform predictions, which could start with the 7 billion meter parameters and even can it's go up to the 321 billion parameters, deploying these models may require an intensive resources and a lot of optimizations rather than using a traditional methods to deploy those models. Then, as I already initially talked about the latency, like when a sentence or token is complicated, the process takes several minutes to complete that tokens. So user's input token is given, then that token is converted to the subwords or subtokenizations. Then positional embeddings will come there, encoding will happen there. Then multi-head attentions, self attentions, all those things will happen. Dot products will happen between key values and all those things. Also, the third important point is the cost. Large scale systems or with multiple LLMs in the systems, which would consume a lot of budget for the applications related to the LLMs and all those things. So, how to reduce all those things, as we have seen so many challenges here. So, the foremost solutions and best solution or easiest solution is the use of VLLM. So what is vLLM doing is there. So vLLM team propose a new method to solve this by using a similar to the OS virtual memory. So many of you are utilizing iPhone, so it's based upon the OS memory. So it's operating by utilizing virtual memory process, which could improve LLM serving performance around 24 times while using the half the memory of GPU compared to the traditional methods. So it will increase performance by 24 times and just reducing the half the GPU memories as compared to traditional methods. And how you can integrate that vLLM into the your system? So simple is vLLM provides a simple inference that led machine learning or AI engineers. So whatever we are studying here, so we can introduce that through the Python inference. So what is the secret behind the vLLM and how it can help to reduce that half the GPU memories and 24 percent increase into the latency, 24 times increase into the latency. So before that, you need to know like how large language models are works and what's happening whenever we send the user request and how multiplications happening, why it's taking so much memory. So large language model is a attention neural network, and most many of you know the transformer, how it's working and all those things. So the most important thing there is like attentions, how you can calculate the attentions. So single head attentions, multi-head attentions, and within that attention, there are three blocks like query, key, and values. So, and how that is calculated. So we are applying this swap to max to the dot products of Q queries values, and we are dividing it by the dimension of the keys. And at the end, we are multiplying it by the values. So we will get some scores. But for to apply only that mathematical equations, it will take huge GPU memories and all those things, because based upon the user input context lens, the multiplication increases quadratically, and it will consume that GPU memory. So in the autoregressive process of the model, it will compute a attention formula to select a keyword as output. The formula consists of three variables, as I mentioned, query. So we will see in details like what is query. So a new token in the decoder step, or the last token that model has seen. So query is the last token as model has seen, or the a new token into the decoder's step. Key means the previous context the model should attend, and values are the weighted sum over previous context. So let's we will elaborate this in more times. So in the meantime, query is a vector of dot product between the embedding and weight, and key and value are the matrices, since they need to store the previous context and the weight sum of previous context, which is referred as the KV cache. So KV cache is the major important factor here. So query is the product dot product between the embeddings and weights. The main reason that model needs to store that key and value is that attention algorithms that needs to process a query variable of previous key and value before generating the new token, which could be a massive compute cost. If it doesn't store the model code, impact the model performance. So it's reduce the number of request and key generation length, since the long text requires a huge KB cache to store. And according to the efficient memory management for large language model serving with the page attention, around 30% of GPU memory is occupied by the KV cache. And these statements may be lead to the another issue about the memory usage. So let's so basically the KV cache of request is stored in the continuous memory space, since many deep learning frameworks compute with the tensor values that needed. I hope my audio is clearly audible. I think I'm stop here. I will give you the details later. But still, yeah, we will completely. Memory fragments, the KV cache is request store continuous memory space, since many deep learning. So vLLM coming here with the page attention. So it's like OS virtual memory. And in simple terms, so one could think of blocks as pages, tokens as bytes, and request as process. So by using KV cache block, virtual memory for storing each token byte from the prompt and making the block table, page tables into physical KV cache, physical memory. Consequently, physical GPU memory will be allocated when the system needs it. In theory, it will eliminate uh, internal fragmentations and external fragmentations, since the token stores the same cache block size and allocates it when the system requests it, which means another benefits of page attention is also using page attention allow the system to share KV caches, since it stores tokens into non-contiguous memory, which led to many applications for LLM. So I hope you have got this some little bit, and I hope my audio quality and clarity was also good here. Else I have need to record once again. Thank you.